So welcome to this masterclass from Cambridge Leadership College. My name is Warwick Bailey. I'm one of the Z coaches at the college. And in this masterclass, we're going to be going through some A2 level work for chemistry with the Cambridge International Exams. We're looking in this masterclass at paper 4. It's the winter series from 2013. And it's a 2-hour paper. And these are sort of short answer or structured questions. Now, it's going to be a challenge to get through the whole of an hour and a half's paper, the whole of a 2-hour paper in a 1.5-hour masterclass. So what we'll do is we'll look at the comments that the chief examiner makes once all the students have completed the Cambridge International Exams, and focus particularly on the areas where the examiner picked out that students had most difficulty. So for things that it's easy to look up in revision guides or textbooks, definitions, for example, that are easy to look up, we'll scan past those pretty quickly and then focus the limited time that we've got on the particular areas that the chief examiner highlighted where students needed to pay attention. And interestingly enough, this first question was one of the ones that the examiner said that students had many problems on, which is surprising because you'd expect actually in the exams for the first question to be an easier one to allow students to enter the exam and get going rather than having an immediately difficult question to work on. So the examiner is saying that this was difficult for students, but if we think about it in a little bit of depth now, I think you'll see that actually it should be a lot easier to handle than some of the difficulties that the students encountered. Okay, so this first question then is looking at this reaction between ammonia and hydrogen chloride. And you can think of this as an acid-base reaction, okay? The ammonia is a base, the hydrogen chloride is an acid, and it's a bit like the hydrogen chloride as an acid is donating a proton to the base ammonia. So if you think about that then, I'll just get my pen working here. So you've got hydrogen chloride here, and you've got your ammonia here. I'll just draw it that way around. And you've got 2 electrons in this bond here, haven't you? That covalent bond is made of 2 electrons. One is from the hydrogen and one is from the chlorine atom. And because this is acting as an acid, it's going to be a proton donor. That means that both of those electrons, one from the hydrogen and one from the chlorine, are going to remain on the chlorine, which is going to become a chloride ion. And you're going to get the H plus proton. It doesn't have any electrons actually. And you've got the chloride anion, which has now got the 7 electrons that belong to the chlorine, and the one that came from belonging to the hydrogen. So you've got 8 electrons there, 7 from the chlorine, 1 from the hydrogen. This is now just a proton, no electrons at all. And back on the ammonia over here, the nitrogen has got a lone pair of electrons, okay? And because the base is a proton acceptor, when the hydrogen ion is accepted by that base, then the new bond that forms is those 2 electrons from the nitrogen forming a bond with the hydrogen ion that came over here. So that's 2 electrons donated from the nitrogen. Both electrons came from the nitrogen. That's a kind of dative bond. And so the bonding is going to be including ionic, covalent, and coordinate, because you've got, that's a result of the base, ammonia, reacting with the proton, and then that has an overall positive charge, of course, and then the chloride ion has got a negative charge. So that's the ionic bonding. The covalent bonding is just the unperturbed bonding between the nitrogen and the hydrogen ions. And then the dative bonding, of course, is the lone pair of electrons that's on the nitrogen forming a dative bond to the hydrogen ion there. So, I don't think that is too difficult to work out. And so when you come down to drawing these dot cross diagrams here, start with a chloride ion, and it's got the 7 electrons that belong to the chlorine atom. 1, 2, 3, 4, 5, 6. And then, if you remember, it's gained 1 electron that used to belong to the hydrogen, because the bond between the hydrogen and the chloride ion was broken, so that the hydrogen atom became a proton ready to donate to the base ammonia. And so that hydrogen ion is forming this dative bond here, and that's the 2 electrons from ammonia. And then the rest are just the covalent bonds that have been unperturbed from ammonia. So that's, well, what do you think? I don't think that's too difficult if you did a little bit of analysis to begin with about acid-base reactions at the top of the page. If you sort of ran through this question and went straight to the diagram without having given a bit of thought like we did up here, then you would get in problems, I think. But with a little bit of forethought, rather than trying to jump into the question too early, then I think that works out fairly straightforward and should be a good, easy 3 marks at the start of the exam. Okay, so these are all fairly straightforward. There's only 1 mark apiece. You can look up most of the answers in the mark scheme. I don't think I should spend too much on that. The one point here, the examiner highlighted that students had some difficulty with. You know from your work on group 2 trends that calcium oxide is more soluble than magnesium oxide. And that's the reason that calcium oxide can absorb more water than magnesium oxide can absorb. And that's the reason that the calcium oxide is used to dry the ammonia rather than magnesium oxide. So you just had to apply that knowledge of calcium oxide being more soluble than magnesium oxide. You just had to apply that known knowledge of group 2 chemistry in that unfamiliar environment there. Incredible. This thermal decomposition of a group 2 nitrate seems to occur in almost every one of these structured answer papers from Cambridge International Exam. So make sure you know that equation, because it gets asked again, again, and again. So just look that up. You can check it in the mark scheme. It's just one of those equations you've got to learn. Same for the thermal stabilities of nitrates. As you go down group 2, they become more stable. Again, that's just something that you can look up in the revision guides or textbooks. They have very good explanations of that. Okay, now we're doing some more work on, I suppose this is in the sort of periodicity part of the course, looking at melting points of group 4 elements, comparing silicon and carbon. Well, they have covalently bonded giant structures. And so to melt carbon or to melt silicon, you've got to break the covalent bonds in the giant structures. And the carbon-carbon bond is much stronger than the silicon-silicon bond. And that's the reason that the melting point of carbon is greater than silicon. These carbon-carbon atoms are closer together than the silicon-silicon atoms. You have shorter bond, greater bond strength. Then a little bit more complicated comparing tin and germanium here. Germanium in the solid has a giant covalent structure. These are covalent bonds. But tin, of course, is a metal, and so that has metallic bonding. And because the melting point of germanium is greater than the melting point of tin, then it means that the covalent bonding in this giant covalent structure of germanium is a stronger bond than the metallic bonding within the metallic tin. Okay, some more equations here, 1 mark apiece. Again, these are things that you can look up in your revision notes, in the textbook. They're covered in the mark scheme as well. I'm not going to spend any time on that. Let's look at this work on Bronsted and Lowry acids and bases. Now, you'll remember your definitions of a Bronsted and Lowry acid. Of course, that's a proton donor. And of course, the converse for that, for a Bronsted and Lowry base, it's, well, of course, it's a proton acceptor. We're saying a proton here, but a proton, of course, is just a hydrogen atom with its single electron removed. It is a proton. In the Bronsted and Lowry definitions, it might be easier to think of this rather than a proton donor or proton acceptor, a hydrogen ion donor, or a hydrogen ion acceptor. Same thing, just in a slightly different language. And so it's throwing you a little bit, because normally in your textbooks, you see the general way of describing a Bronsted and Lowry base and Bronsted and Lowry acid is by having an HA. That's the Bronsted and Lowry acid there. And they've just changed that. Instead of saying HA, they're saying HZ. Means exactly the same thing. Don't get thrown by that. So here's the ammonia base, and here's this Bronsted and Lowry acid. And an acid is going to donate the hydrogen ion to the base. So the hydrogen ion H+ is going to the base, NH4+, leaving the Z- there. That's the first one. Next one here, you've got, again, your Bronsted and Lowry acid here. It's going to donate a proton. It's going to donate it to the methanol there. So that becomes, you just got to hold your nerve here, because these things look a bit unusual. CH3OH2+, you're not familiar with that perhaps. But you just got to hold your nerve, because you know that the Bronsted and Lowry acid is this hydrogen ion donor, or this proton donor. So all it's doing is donating a hydrogen ion to the base, which accepts the hydrogen ion. Similarly here, you're now going to have some things that look unfamiliar, and you've just got to hold your nerve and just know that a Bronsted and Lowry base is a proton acceptor. So in the first one here, well, this Bronsted and Lowry base is going to accept a proton. So B- with the H+ gives you that. Where did the proton come from? It came from the ammonia molecule. And because the ammonia molecule has lost a hydrogen ion, we're going to have 2 there, aren't we? And it's going to have a negative charge. Again, this looks unfamiliar, but you just got to hold your nerve, knowing that the Bronsted and Lowry base is a proton acceptor, hydrogen ion acceptor. Same for this one here. The base is going to accept a hydrogen ion, and that must mean that the methanol here has lost a hydrogen ion. It's donated it. So that gets a negative charge on there. Okay, so these things you can look up because you've got some definitions to give here. The point that the examiner was looking for in the dynamic equilibrium was to do with when you have a forward reaction and a reverse reaction. This equilibrium is when the rate of the forward reaction is exactly matched by the rate of the reverse reaction. And so the mixture has a constant composition. If you measure the composition at any particular time after equilibrium has been attained, the mixture would have the same composition, the same concentrations of A and B and C and D. But at a microscopic level, A and B are still changing into C and D are still changing to A and B. It's a dynamic, continuous change from A to B to C to D. But because the rates are exactly equal, you end up with this constant composition, this equilibrium composition, or you might say a position of equilibrium. Okay, again, we're going to rattle through this buffer solution. You can look that up, just to understand what that means. And then this part 2 down here, again, the examiner said that students answered this quite badly. So for a buffer solution has a mixture of a weak acid and its conjugate base. So in a buffer solution, you typically have about the same amount of acid, weak acid, as you do its conjugate base. So you might have 0.5 of a mole of this and 0.5 of a mole of that conjugate base. And what happens is that if you add more acid, hydrogen ions, all that happens is the hydrogen ions that you added then just get bound to the conjugate base and form the undissociated acid over here. And so that uses up the additional acid that you just added. And in that way, the solution is buffering against the acid that's been added. And if you add alkali, well, then the hydrogen ions there and the alkali that you've added just neutralize and make water. And because you've got an equilibrium here, as that hydrogen ions are used up, then just more of the undissociated acid dissociates and provides hydrogen ions to take the place of the hydrogen ions that have been used up. And for those two reasons, the pH of a buffer remains about the same when you add a small amount of acid, hydrogen ions, or you add a small amount of hydroxide ions and alkali. Okay, so that was a lead-in really to talking about weak acids. And you've now got to take this weak acid here, propanoic acid, and you've got to calculate its pH. So what's happening here is you've got your weak acid, which has been dissolved in water, and just a small amount of it dissociates. Not very much. It's a weak acid. It doesn't completely ionize. It's just partially ionized. And if you wanted to make that clear, you could rewrite this equilibrium here to show that actually the position of equilibrium lies well over towards the reactant. Only a little bit of it dissociates. And you can write an equilibrium constant for that. And that special equilibrium constant, Ka, is then equal to that's the propanoate anion and the hydrogen ion concentration divided by the equilibrium concentration of propanoic acid. Now, in some questions, they haven't done it here, they ask you what assumption are you making in doing this calculation, because if we weren't watching very carefully, these are all equilibrium concentrations, but we only have an initial concentration for the propanoic acid. We don't actually know its equilibrium concentration. And so we're making an assumption that because such a tiny amount of it actually dissociates, its equilibrium concentration is virtually the same as its initial concentration. So if we know the initial concentration, we can make an approximation that the equilibrium concentration is the same as the initial concentration. So that's one assumption we're making. The other assumption we're making is that these hydrogen ions here only come from the dissociation. Now, you may know that water itself dissociates. So there's a small number of the hydrogen ions that contribute to the pH that are coming from the dissociation of water. But that's something that we're going to ignore as well. We're assuming that all these hydrogen ions here come from the dissociation of propanoic acid. Now, we know Ka, we've got that, haven't we? It's up here. And we know, or we're approximating this, we're saying that that is, that equilibrium concentration is so close to the initial concentration, we can regard it as being the same as the initial concentration. So we've got two terms. We're trying to find the hydrogen ion concentration to give us the pH. So we've just got this term here. We don't know anything about that, except, look carefully, the hydrogen ion concentration and the propanoate anion concentration have to be the same, because there's a dissociation here, and for every hydrogen ion that's produced, there's a propanoate anion that's produced as well. So the concentration of hydrogen ions and the concentration of propanoate anions is the same. So you can, and this is an approximation, this is a real perfectly valid step to do, is to say, well, actually, that's the same as the hydrogen ion concentration squared, because those two concentrations were the same. And now we've got two knowns and one unknown, and so you just have to rearrange that so that the hydrogen ion concentration squared is equal to this acid dissociation constant times this equilibrium concentration of propanoic acid, and we just assume it's the same as the initial concentration. So we've got that. Of course, we don't want the square of the hydrogen ion concentration. We want the hydrogen ion concentration itself, so we can give ourselves a square root of that. We can calculate now the hydrogen ion concentration, and once we've got that, then the pH value is the negative logarithm to the base 10 of the hydrogen ion concentration that we've calculated. And you do all those steps. You don't need to say what the assumptions are here. Some questions in other exams might ask for it. And you work out the pH value based on the hydrogen ion concentration that you calculated. Okay, keeping on going now. We've got this reaction here. You've got sodium hydroxide and propanoic acid. We're neutralizing the acid, aren't we? Acid and base makes a salt and water. The salt is sodium propanoate and water. We've made a salt and water. Now what's happened is we took 0.03 moles of sodium hydroxide, and we've added it to 100 centimeters cubed of 0.5 mole per decimeter cubed propanoic acid. If you work that out, you end up that the amount of propanoic acid is 0.5 moles. And so if you react those together, then which reactant is in excess? Well, it's pretty easy to see that the propanoic acid is in excess. And so what's happened is that once the reaction's over, that's the initial amounts, and this is the final amounts. I've got N for amount, F for final. Then all the sodium hydroxide has been used up, and you've made 0.3 of a mole of the salt, sodium propanoate, and you've got 0.02 of a mole of propanoic acid in excess. So you just worked those out by looking at this neutralization reaction here. And these are your amounts, okay? But those amounts are in 100 centimeters cubed. And so the concentration per decimeter cubed is going to be 0.2 moles per decimeter cubed of the propanoic acid and 0.3 moles per decimeter cubed of the salt. the sodium propanoate. So just fill those in. Propanoic acid is, you've got 0.2 moles per decimeter cubed of that, and sodium propanoate, you've got 0.3 moles per decimeter cubed of that. So now you've done that little calculation, you've got to work out the pH of the buffer solution. Some of you may know some fairly, or you may recall some equations that allow you to calculate this easily. But really, all you've got to do is use your expression of the acid dissociation constant again, where you've got the hydrogen ion concentration, the propanoate anion concentration, and the propanoic acid concentration. Now, look very carefully. You've got that, haven't you? Because you calculated it up here. You've got this one down here because you calculated it there. You've got that, and so it's true that you've got only one unknown. All the other values in this expression here are known. So we can just rearrange to give us the hydrogen ion concentration as the subject of the equation. You've got the propanoic acid there, divided by the concentration of the propanoate anion. Okay, you know that, you know that, you know that. That gives you the hydrogen ion concentration. And just as you did before, the pH value is the negative logarithm to the base 10 of the hydrogen ion concentration. All right, so again, I think the examiner pointed out that some students had some difficulty with this one here. I think probably the way to work on this is to look over here and just identify what this target, what this endpoint for this synthesis is, and then work backwards. Generally, that's quite a good approach for all working out the synthetic routes. Start with the target, work backwards. And what you can see here is that this linkage here is an ester, isn't it? You know, you have to be able to look at these skeletal formulae and try and see the familiar functional group in there. That's an ester in there. And so to make an ester, you can do that by reacting with an acyl chloride. All right. Now, if I've just got a bit of room on here, haven't really got that much space, but basically, what's going to be happening here is you're going to be taking an acyl chloride, which is that, and you're going to be reacting it with this phenoxide anion. Okay, that's O minus Na plus. And this is phenoxide anion. And the mechanism is, it's called an addition elimination mechanism. So the first step is that. Just give myself a bit more space over here. And that's going to give you that's a carbon there. And then you started to build up what's going to become the ester link. And then that's the addition step. That's a nucleophilic addition, isn't it? Because that's slightly positive there. And then in the elimination step, then the carbonyl group is going to reform and the chlorine atom is going to leave as a chloride ion. And you end up with then which actually is this here. All right. So to make this ester, you reacted the phenoxide anion with this acyl chloride. Okay, that's how you did it. And so this intermediate in here, G, is going to be your acyl chloride. So that's your acyl chloride. Now, you're not given that, so you have to make it in this first step here, and you can use phosphorus pentachloride, or it's called thionyl chloride, to convert the carboxylic acid into the acyl chloride. Sorry about my pen here. It's one of those two. Okay, it's either or, not both. Okay, so that's you can see, can't you, that we've worked backwards. We started with our target, and then worked out that we needed an acyl chloride, and then the acyl chloride itself is made from this starting point, the carboxylic acid. And you can see at the end here, you've got this last piece to figure out. You can see in this last point, part of the mechanism, that the chlorine atom has been eliminated as a chloride ion, and this phenoxide here was this O minus Na plus, and we just use the O minus, the phenoxide anion here, and that means that actually a spectator, well, that's been the spectator ion, nothing's happened to that. The chloride ion was produced in this reaction, and so you've got a sodium ion left over from here, and you've got the chloride ion that's being released at the end of that mechanism there, and so this sort of byproduct is sodium chloride. This is just the definition. You can look that up. The trend in the bond energies is that the CF bond is much stronger than the C chlorine bond, which itself is much stronger than the carbon-bromine bond, which itself is much stronger than the carbon-iodine bond. Okay? And so the relationship between those bond energies, excuse me, is that as the bond energy decreases, then it's much easier for that bond to be broken and for the halogen of a halogenoalkane to be substituted. So the relationship is that as the bond energies decreases, these are decreasing bond energies, then the reactivity is going to increase. Just so, and bear that in mind, because that's a kind of key that unlocks the rest of this question later on. And this is the part that it starts to unlock. So you've got some reactions here, and in the boxes over here, this X means that out of the two halogens, one remained on the molecule, and the other one reacted. So that's why this work up here is important, because you've got to work out down here which one is the most reactive out of the two halogens that have been offered to you in the question. Okay, so look at this then. You've got a halogen there, haven't you? I've lost my pen. You've got a halogen there, and you've got a halogen there, and only one of them is going to react. So you've got to figure out, well, which one is the most reactive? And if you look here, then that carbon is has a there is going to be more susceptible to nucleophilic attack than that carbon there, because that carbon there isn't quite as positively charged. It's only got one chlorine atom on it there. And so for that reason, that chlorine atom is going to be the one that's going to be replaced. This is, again, we saw this earlier on, didn't we? This is an example of an acyl chloride. And so when that reacts with water, then that chlorine atom at the end there isn't going to react. And the reaction of acyl chloride with water gives the carboxylic acid. Next one, you've got to choose between these two halogens. Now, one of them is going to get left behind. Which one is going to react? Well, we looked at that earlier on. I said that was the key that unlocked this question. The bond strength between carbon and iodine is less than the bond strength between carbon and chlorine. So that's the stronger bond, that's the weaker bond. And if we had to choose between these two halogens, well, that's the bond that's going to be most reactive. It's the weaker bond, that's the stronger bond. And so the result of that one is you're going to get the iodine replaced. Coming down to this last one here, well, which bond is going to be reacted there? Well, water is a weak nucleophile. Now, you've got electrons being withdrawn towards the bromine there. So there is a slight positive charge on that carbon there. But here, you've got this delocalized ring system. So anything that gets attracted to that is being attracted to an area of negative charge density. So to attack that carbon there, you need an electrophile, don't you? And here, well, water is only a weak nucleophile, but it's at least it's a nucleophile, so the water is going to attack that carbon there. It certainly can't attack the ring system here, because that would require an electrophile to attack it. And so if you had to choose between these two halogens, well, that's the one that's going to react with water as the weak nucleophile. Nothing's going to happen here, because we need an electrophile to be attracted to the ring system in that arene there. So you end up with like this. Excuse my drawing. And you've got that reacting and that one not reacting. Okay, this is an area of work that the examiner keeps flagging up, that students are weak when it comes to these radical reactions, not with the initiation step or with the termination step, but with the propagation step. And we'll have a look at that in a moment. But you know from your work on the halogenation of alkanes that you need ultraviolet light to start this reaction, or possibly you could have temperatures greater than 300 degrees Celsius. But you know, that's an acceptable answer in the mark scheme, but really most of the time that you're thinking of doing this process, you're thinking of initiating the reaction with the homolytic fission of the bond in the chlorine molecule there with ultraviolet light. And it's going to be a radical reaction. And because you're replacing one of the hydrogen atoms there with a chlorine atom, that replacement is a substitution. So it's a radical substitution reaction. And you can do a little bit of work here because you can work out the enthalpy change, can't you? Because you can work out the enthalpy change, which is the sum of bond energies broken minus the sum of the bond energies from bonds that form. So you just got to do a little calculation there to work out the enthalpy change. And when you do that, you end up with an exothermic enthalpy change there, and you end up with an endothermic energy change there. And this one down here, this is the kind of thing that examiners asking students to particularly pay attention to, because everybody gets that part, which is the initiation, and everybody gets that part, but it's this propagation here that is generally weak. So that's the propagation step. And that's the termination step. Okay, this is easy, isn't it? All you're doing is breaking the covalent bond that joins these two chlorine atoms together in the chlorine molecule, and that's broken through homolytic fission. One electron goes to one chlorine atom, the other electron from the bond goes to the other chlorine atom, and so you end up with two chlorine atoms, each of which have got one of the electrons from the bond. And then that chlorine radical can then react, and you can see here that one of the hydrogen atoms has now formed hydrogen chloride, leaving this radical here. And so that radical can then go on to react with another chlorine molecule, and so we end up with the desired product. And we've regenerated the radical. So you can see in these two steps here, we've got the desired product, but we started with a chlorine radical and we ended with a chlorine radical, and that's why it's called a propagation step. It can keep going. But eventually, you're going to get a termination step, and that means that that radical there can combine with that radical there to form, again, the target compound here. So you've got your radical that you produced earlier on, and you've got your chlorine radical, and those can join, form a new bond between them, and that's a termination step. Okay, so some easy stuff here. Examiner said that most students were comfortable explaining polymerization, and that because you've got this double bond here, then the type of polymerization is addition polymerization. Okay, so I think this is all fairly obvious from the mark scheme. Just need to look at this bit here. Okay, so what you want to remember here is that when you've got a carbon-carbon double bond, that's so-called sp2 hybridization, and when you've just got normal carbon to carbon bonds, that's an example of sp. Carbon has atomic number 6, so it has this as its ground state. That's the 1s2, that's the 2s2, and this is that's 6 electrons altogether, isn't it? So that's the p orbitals there. And what happens to get this so-called sp2 hybridization is that you go from the carbon ground state to a carbon excited state, nothing happens to the inner electrons, but one electron is promoted, so you ended up with that. And once you've got that excited state, then you can have a hybridized, I don't have room to write it here, but the hybridized state means that that 2s orbital and two of those p orbitals hybridize, leaving one p orbital behind. So I'm just going to try and continue writing it down here. So that's, nothing's happened to the 1s orbital, but you've now got sp2, and you've got one p orbital, let's say, left behind there. Okay, and so at that point, then what happens is the carbon atom can form 3 sigma bonds, because each of these hybridized orbitals can overlap to form a sigma bond. And then you've got this one electron that's left in the p orbital, so that's just left there like that in its p orbital. And if there's another carbon atom here that's similarly sp2 hybridized, then you get this sideways overlap between them. So in this sp2 hybridization, you can see that you ended up with these 1, 2, 3 sigma bonds, and they arrange themselves in space to be as far apart as possible to minimize the electron-electron repulsion. And so you end up with a 120-degree bond angle between those 3 bonds, and that's trigonal planar, you'd call that shape. Okay, so that's what's happening when you have this carbon-carbon double bond. There's one sigma bond, and then there's this sideways overlap from these p orbitals that were left over from the hybridization, and that sideways overlap gives you the double bond there, the pi bond. So that's the sigma bond, and that's the pi bond, even though we draw them the same in the carbon-carbon double bond. When it comes to carbon-carbon single bonds, you've got exactly the same ground state for carbon. You've got exactly the same excited state, but you get a different hybridization. Nothing happens to the 1s, but all 4 orbitals, the p orbital, sorry, the s orbital, and the 3 p orbitals now all hybridize, and you end up with 4 hybridized sp3 orbitals. And so they're now ready to make 4 sigma bonds and to arrange themselves in space to minimize the repulsion between them. Then those bonds arrange themselves in space in this tetrahedral arrangement. I've just drawn it there with the carbon in the middle. 2 bonds in the plane of the paper, 1 bond coming outside towards me from the plane of the paper, and 1 bond going behind the plane of the paper. And the bond angle there is 109.5 degrees. And so the angle is changing from 120 degrees to 109.5 degrees. And the explanation is that you're going from sp2 carbon with trigonal planar geometry to sp3 carbon with tetrahedral geometry. Okay. Okay, there's a good description in the mark scheme about how the hydrogen bonds form there. And you can look that up. I'm not going to go over that. Similarly, the mark scheme explains well what happens to the observation when water is absorbed. As water is absorbed, the concentration of the copper sulfate solution increases, and as the concentration of the copper sulfate solution increases, then that appears to you. Your observation is that you get a darker blue because you have a more concentrated solution of copper sulfate. You have to remember a lot of these questions have a flow to them. They're kind of an early part of the question is putting some thoughts in your mind that you're going to use later in the question. Okay, so in here, you see, you've got a small molecule, but it has two functional groups. Now we'll come to that later in the question, but the functional groups are, well, you've got an alkene there, haven't you? And then you've got, if we drew this out as a displayed formula, okay, that's the fully displayed formula there. That's the alkene, and this group at the end with a carbonyl group and this NH2 here, that's an amide. Okay, so you've got alkene and an alkene and an amide. Okay, I want to make sure there's something I wanted to cover down here particularly. Okay. I think the mark scheme covers this next bit quite well. You can just look that up. Okay, let me talk about these protein molecules formed by polymerization of amino acids. So I just need to get. All right, so the thing about amino acids, and it's not very clear from the way they've drawn them here, but every single amino acid has a kind of core structure. And the core structure is the amine group joined to a carbon, which is joined to a carboxylic acid group. And because that carbon in the middle there needs 4 bonds, there's always a hydrogen. So that's the common pattern for all amino acids, with some group here that distinguishes one amino acid from all the others. So, yeah. Okay, in the case of glycine, actually that group there is just a hydrogen atom. In the case of serine, then the group there is that, isn't it? In the case of valine, the group is that. And we can't see the hydrogen atom, but it's implicit there. Okay, so that's the thing, is you just need to get your head around that there's this very simple repeating structure in all amino acids. You've got an amino group, you've got a central carbon atom, you've got a carboxylic acid group, and you've got a hydrogen atom, and then you've got something else as another substituent there, and that's what distinguishes one amino acid from another. And you've got to draw a tripeptide. So the easiest way to do that is to remember you've got this repeating pattern. Okay, we'll fill in the side chains later on, but at one end you're going to have the amine group, then you've got that, haven't you? And then that comes down to the carboxylic acid group, and that's going to be forming an amide bond, which then goes down to the and this is the carbon here that's going to have the side chain. And because it's a tripeptide, it ends with the carboxylic acid there. Okay, so that's the, if you're drawing this, probably knowing that general structure of amino acids and then getting that structure in place to begin with just means you're not going to get sort of mixed up when you're drawing this. Okay, and now we've got our structure in place, we've got to add on our side chains at those points there. Now, so serine, where's that up here? So that had that side chain, didn't it? So that's going on there. What's the next one? Glycine, well, that just had a hydrogen atom. I'll draw it in, but in a skeletal formula like this, you shouldn't be drawing in the hydrogens. I'll leave it in for the moment. And then the last one is valine, and that had this group there. Okay, so I've drawn there, haven't I, the skeletal formula, and that would be correct if I just remove that. But the question is asking for displayed, which means you're expected then to show all the atoms and all the bonds. But I'm trying to emphasize that you can draw these peptide chains, or this tripeptide with these amide bonds in it, by knowing that structure of the amino acid and then drawing them. So you've always got a carbon in the middle where the side chain is, and then the carboxylic acid. And then you've got the carbon in the middle and the carboxylic acid. You've got the amine, carbon in the middle, and the carboxylic acid. You know, if you're sort of disciplined about your drawing, you can get that right. Okay, let me try and get through here. Okay, this is a question about a non-competitive inhibitor. So the non-competitive inhibitor doesn't fit into the active site of the enzyme. What it does is it binds to somewhere else on the protein chain of an enzyme and then causes the active site to be distorted. And when the active site is distorted, it doesn't have the same catalytic power, and so the rate of reaction from a distorted active site is less than the rate of reaction from an undistorted active site. And so we'd expect the rate of reaction to be lower when there's a non-competitive inhibitor present. So we're expecting the rate of reaction to be lower, a graph to be at a lower value on the rate of reaction axis. Now, the reason this is plateauing is because as you add more and more substrate, all the active sites have got filled up. So you eventually reach a plateau, and no matter how much more substrate you add, it doesn't matter, because all the enzyme active sites are already saturated with substrate. So we're expecting a same kind of shape, but at a lower rate of reaction, because the competitive inhibitor has distorted the active site, and so the catalytic action isn't as strong as it was without the competitive inhibitor, non-competitive inhibitor present. And so we're expecting to see a graph a bit like that, plateauing as well, because eventually all the active sites, even though that they're distorted, become saturated with substrate, and it doesn't matter how much substrate we add, it doesn't affect the rate of reaction. The active sites are saturated. Okay, the mark scheme talks you through electrophoresis. That's quite clear. Now, I wanted to spend a bit of time on this work on partition coefficient. Okay, now the thing is, just in the same way when we were dealing with buffers and acids and bases, Bronsted-Lowry acids and bases, you know, all of these things can be understood by using different forms of an equilibrium constant. And so what's going on here is they're saying you might have a compound X, which is dissolved in an organic solvent. No, get that the other way around. You've got a compound X, which is dissolved in an aqueous solvent, and X can also dissolve in an organic solvent. And so if you have an aqueous solution and an organic solution, those are immiscible. They won't mix. If you drew them in a separating funnel like this, I'll just put a tap in there at the bottom, then the aqueous phase would be the more dense, usually, at the bottom there, and the organic phase would be immiscible and less dense above it. And you can have X, which is soluble in the aqueous phase, and X, which is soluble in the organic phase as well. And depending on whether X is more or less soluble, you can have more of it dissolved in the organic phase or more of it dissolved in the aqueous phase. And you've got a dynamic equilibrium with these particles of X continually moving from the organic phase into the aqueous phase, and from the aqueous phase back into the organic phase. And because you've got an equilibrium here, you can write an equilibrium constant. And you can have that equilibrium constant in terms of concentrations. And so the equilibrium constant for this little equilibrium here is the concentration of X in the organic phase divided by the concentration of X in the aqueous phase. And when you set up an example like that, that equilibrium constant is just called, it's just changed its name, it's called the partition coefficient. But all it is, it's a special case of an equilibrium constant. So the language that the examiner was looking for was you could draw a diagram, or you could draw an equation that's really good for explaining this, and the examiner is looking for something that says, well, the partition coefficient is an equilibrium constant of the ratio of the concentration of a solute in an organic phase and an aqueous phase. So you're looking for these keywords for concentration and ratio of a solute dissolved in an organic phase and an aqueous phase. Now you come down to some calculations here which are a little bit tricky, but if you hold your nerve and just work with normal rules of working with equilibria, concentration calculations, then it works out quite nicely for you. Because when we go through these papers, I've generally encouraged students to work with what's called an equilibrium table, which is a really solid way of trying to work out all sorts of calculations where you have equilibria. So you've got this X solute, which is in the organic phase. Sorry, I keep getting that wrong way around. That's the aqueous phase there. And that's in equilibrium with the same solute in the organic phase there. And there's this partition coefficient, or this equilibrium constant, that helps us understand the position of equilibrium. Is the solute more or less dissolved in either of those phases? And because this is an equilibrium, you can write one of these equilibrium tables, which has this mnemonic ICE. I for initial, C for change, E for equilibrium. And so we're told, aren't we, that initially, the initial situation is you've got 4 grams of X, and that's dissolved in 0.5 decimeter cubed of water. Now, you then add this ether here, ethoxyethane, and that 4 grams that was just originally only in the aqueous phase is now going to get partitioned between the aqueous phase and the organic phase. Now, at the moment, we don't know how much of it has gone from the aqueous phase to the organic phase. All you can say is that some of it, let's call it little x, has left the aqueous phase, and the corresponding amount has gone into the organic phase. And so that's the change you'll see in this equilibrium table. And so the equilibrium amounts are the 4 grams that we started with minus the amount that's gone into the organic phase and the amount that's in the organic phase. So those are our masses that have gone into the different into the organic phase and left behind in the aqueous phase. And the volume was 0.5 decimeters cubed for the aqueous phase and 0.05 decimeters cubed for the organic phase. And so the concentration for the solute X in the aqueous phase is 4 minus X divided by 0.5. That gives us our concentration. That's grams divided by volume. And here you've got X grams, and that's now in 0.05 of a decimeter cubed. And so at that point, you can start using your equilibrium expression, and you've got the equilibrium constant, or the partition constant, is equal to the concentration in the organic phase, yes, divided by the concentration in the aqueous phase. We derived that or explained that earlier on. Substituting our numbers in, we know that this equilibrium constant, that's called the partition coefficient, is equal to 40. And you've got that concentration divided by that concentration. Okay, you just got to hold your nerve here because it's looking a bit messy. All right, and all you've got to do there, because you're trying to find out this value X, what mass of the solute has gone into the organic phase. And so you just need to do a little bit of mass there, where you've got, I'm just rearranging it here. You've got that. And you can start to cancel some things here. And basically, you've got just a little bit of maths there, and you end up with X is equal to 3.2 grams. So out of the 4 grams that was originally in the aqueous phase, most of it, actually, the position of equilibrium is to the right, most of it, 3.2 grams, has ended up in the organic phase. Now, once you've worked through that once, it becomes much easier to work through it again, because they're contrasting, aren't they? Just doing the partition once with 0.05 decimeters cubed of the ether, or doing it with the total same volume, but doing the partition twice, each with 0.25 of a decimeter cubed of the ether. So because you've worked out that expression once, now for this example, you've got the partition coefficient is equal to X divided by 0.025 this time, because we've got a smaller volume of ether, over 4 minus X divided by 0.5. So it's exactly the same as the calculation you had before, except you've got a smaller volume of ethoxyethane. And when you do that calculation, you've got to do a bit of maths there to work that all out. You end up with only not 3.2 grams as we had before, but you end up with 2.67 grams. Okay, so that's the first step. Now the second step is, well, if you started with 4 grams in the aqueous phase and you removed 2.67, then the number of grams that are left in the aqueous phase is now 1.33 grams still left in the aqueous phase. So that's the first step. The second step is you're going to write out this expression again. There's your equilibrium constant, or your partition coefficient, and you are using another 0.025 decimeters cubed of the ether, ethoxyethane. But this time, sorry, that's my X there, you've got 1.33 grams minus X, and you've still got 0.5 decimeters cubed of the aqueous phase. And again, you've got to do a bit of maths there, and if you work your way through that, then you find that the amount of solute X that ended up in the organic phase ends up as 0.0887 grams. And so the total amount of the solute that was transferred from the aqueous phase into the organic phase is that plus that. And what I want you to notice is that the key to unlocking this question was setting up a nice little equilibrium table that allowed you to construct this little bit of maths over here. And it's very common that these questions that require you to use an equilibrium table are mark rich. You've got here, oh my God, you've got 4 marks for this work here. I think actually you've got to work quite hard for that, but it's a general rule that these equilibrium type calculations with these equilibrium tables, if you can use them, will reward you well in terms of marks. They're quite mark-rich questions. Okay, now there's one more thing, because I'm running out of time, but one more thing that I wanted to cover on this that I somehow managed to skip earlier on, because it was something that the examiner flagged up the students had difficulty with. Just one moment while I try and get this to work. Let me see. Okay, oh, that's the one up here. Okay, so this monomer here, you can see that it's got 2 different functional groups. It's got an alkene and it's got a carboxylic acid. And so they're asking you to come up here with a systematic name of that molecule. I just needed to go over that in this masterclass, because that was something that the examiner picked up that most students had difficulty with, because what's happening here is you've got that functional group and you've got that functional group, and there's other hydrogen atoms here, aren't there? And your difficulty is, how are you going to name that, because you've got these 2 functional groups? Are you going to name it as an acid, or are you going to name it as an alkene? And the UPAC rule for this is that the carboxylic acid group takes, or in the language of naming, takes precedence. Okay, the naming is going to be driven by the carboxylic acid group, not the alkene group. Now, if we take a slightly more easier one example to see, if you had that, you've got 1, 2, 3, 4, 5 carbons. So that's going to be pent something, isn't it? And you've got a carboxylic acid there. And so the naming of that is that the carboxylic acid group takes precedence. So you're going to start your numbering from the carboxylic acid group. So that's number 1, number 2, number 3, number 4, number 5. So that's that's a 3E, isn't it? Okay. So the naming for something like that, where the carboxylic acid group is taking precedence, is pent, because you've got 5 carbon atoms, and you want to say pentanoic acid, but you can't say that because there's this ene group in there. So instead of saying pentanoic acid, you say pentanoic acid. All right, so that's pentanoic acid, and because the ene, the alkene bond there, is at carbon number 3, it doesn't have precedence. The carboxylic acid has precedence or has priority. So that would be 3-pentanoic acid, pentanoic acid. And so when you come back to this one here, the carboxylic acid takes priority or precedence. That's number 1, that's number 2, and number 3. So you've got 3 carbons in a chain. That's going to be not a pent, but it's going to be prop, isn't it? And so that is going to be propenoic acid. Now, and the ene part, the alkene part there is at carbon number 2, so you could call that 2-propenoic acid. But actually, when you look at the mark scheme, they don't include the 2 because there's no ambiguity about where the alkene functional group is. Here, there could be some ambiguity, so you correctly write 3-pentanoic acid. And here you write propenoic acid. 2-propenoic acid would be systematically correct, but it's unnecessary, and you remove the 2 because it's not adding any extra information. Because if you've got such a short carbon chain, then it's clear that the carbon-carbon double bond must be at position number 2. And that's the naming convention for when you have a carboxylic acid and an alkene in the same molecule. The carboxylic acid takes priority. It gets labeled number 1. And you can see there that when you have ambiguity about where the alkene might be, you can remove that ambiguity by using the numbering system based on the priority of the carboxylic acid having number 1. That's pentanoic acid, and this is propenoic acid. Okay, well, that's this masterclass really complete for this structured question exam paper from Cambridge International Exams. If you do have any further questions, then the Z coaches from Cambridge Leadership College will be absolutely delighted to follow up any questions that you have on the Slack channel. So make sure if you have questions, you put them on the Slack channel, and the Z coaches can follow up with you there. And so it just remains for me to say, I wish you every success in your chemistry studies, and look forward to joining you again for the next Cambridge Leadership College Masterclass.